In this video, we're going to do another example of using the fundamental counting principle with probability. Use the fundamental counting principle to calculate the following probabilities. Write your answers as percents rounded to 2 decimal places. So let's look at the question. Tom is creating a 3-character passcode. The first character must be a digit from 0 to 9. The second character must be a letter from A to Z. And the third character must be from the set of special characters. So this is a set, and there's 1, 2, 3, 4, 5 elements. So let's just write 5 elements in here. And the first question we're asked is how many 3-character passcodes are possible? So this is going to be our sample space for all the probabilities, so we want to find what that denominator is. So notice we have 3 choices, 3 decisions we need to make. We need to choose a digit, a letter, and a special character. But the number of options per choice is different for each one. Options per choice. Okay, for the digits, we have the digits from 0 to 9. Notice that's 10 digits. Letters from A to Z, there's 26 letters in the alphabet. And there are 5 special characters that we have to choose from. Okay, so the total number of 3-character passcodes, this is 50 times 26, is 1,300. So there's 1,300 different ways we can do this. Okay, let's look at the next question. Tom chooses all of the characters at random. What is the probability the passcode starts with a 1? So now, our denominator, and again, I'm going to write this as, you'll see why in a minute. I'm going to write the denominator as 10 times 26 times 5. Okay, and now I'm going to find the number of ways to make the specific passcode where it starts with the digit 1. So we have a digit choice, I'll just write D, a letter choice, and a special character choice. So this product with the passcode starting with 1 is going to be the size of our event space. So if it starts with a 1, well, that's just one of the 10 digits. Letters, it doesn't say anything about letters, so we still have 26 choices and 5 choices for the special character. So this product goes in the numerator. And maybe now you see why I haven't multiplied it out. We're actually asked for a percent, so we don't have to simplify this fraction. Okay, but notice we have a 5 in the numerator and denominator. They cancel the 1. The 26's cancel out. Okay, and we're left with 1 over 10, which as a percent is 10%. Okay, and yes, you can compute this on your calculator, but sometimes it's useful to do it this way because you can see that a lot of the options haven't changed, so they've just canceled each other out. And notice the passcode starting with a 1, well, that's independent of the letter or the special character, and 1 is 1 out of the 10 digits. Let's look at the next one. Tom chooses all the characters at random. What is the probability the letter is a T, O, or an M? So we have, okay, again in the bottom we'll have our 10 times 26 times 5. We'll have for our event space the digit, the letter, and the special character. Okay, so it doesn't say, let's highlight this, so this is just talking about the letter. Okay, for the digit we still have 10 choices. For the letter, instead of 26 choices, we have 3 letters, T, O, or M. And for the special character, we still have 5. So 10 times 3 times 5 in the numerator. Okay. And notice we could punch this all in, but the 10's cancel, the 5's cancel. So we really just need to find 3 out of 26. I'm going to multiply that by 100%. Don't know this one off the top of my head. So 3 divided by 26 times 100. So that probability is 11.54%. And now let's look at our last question. Tom chooses all of the characters at random. What is the probability that the passcode is exactly 7K $? So you may see this directly, but notice this is giving us a specific value for each of the options. Okay, so it's restricting everything, the digit, the letter, and the special character. So there's only one way to get SK $, and to show that, there's one way to get S, 1 out of 26 ways to get the K, the letter, and 1 out of 5 ways to get the $. So this is 1 divided by that original number. I believe that was 1,300. And let's write it as a percent. So 1 divided by 1,300 times 100 equals, so that's 0. It's very unlikely. Oh, went away. We'll go to 2 decimal places, so 0.08%. And again, notice this is a percent. Don't move the decimal. We already multiplied by 100. Okay, so any individual outcome would have a chance of 1 in 1,300, which happens to be approximately 0.08%.